Alright, Mr. Palmer here. I'm going to try record this D-type flip-flops video a second time. Hopefully a bit better this time around. Okay, so basically before you go through this video, make sure you've gone through your truth tables on so you know your AND or not. Also really important, your XORs and your NANDs. Okay, so by the end of this video you should be able to explain what sequential logic is, what we use flip-flops for, why we use them, and you should be able to basically explain how the output of a D-type flip-flop is calculated. So first of all, what is sequential logic? Basically, sequential logic is obviously not combinational logic. All right, there's two types of logic we're concerned with. Combinational logic refers to that in like the like you'll see in adders and in the kind of traditional logic circuits that you're working out. Sequential logic is the digital logic that we use in Boolean circuits, where the output basically is a function of the sequence of inputs. Okay, what that means is that sequential logic circuits have memory, and you should be thinking to yourself, memory, right? Memory, computers, quite important. Yeah. So we're going to have a little analogy first, so you can kind of understand what I'm talking about when I keep saying that sequential logic is a function of the sequence of inputs. So if I'm driving my car and I'm in first gear and I select up on my shifter, the gearbox is going to shift to second. Likewise, if I'm in third and I select up, the gearbox is going to shift to fourth. That means that, right, the gearbox is storing the current gear as a part of its state. And if I'm in fourth and I select down, the gearbox needs to know what inputs have been received thus far to know where it's at in order to calculate where it needs to go to next. Okay, so the output of gear selection is a function of the sequence of the input history. Obviously, you can replace the bit in red with anything that is going to be using sequential logic. So a couple of other things we need to know about before we start looking at some sequential logic circuits and flip-flops. All right, so a big component of the computer that we're concerned with is a clock. All right, that's a definition of what the clock is. You can Google it and you can just look up clock on a motherboard or something. You will see that there'll be like a little chip with a crystal next to it. Okay, on a motherboard. You can even have a look in your machine afterwards and have a look and see if you can spot it. And that's basically the circuit that's producing that timing signal. Okay. In this video, we're going to be concerned with square waves when we look at the operation of D-type flip-flops. Now, the wave might look like this. We've got a low, zero, and a high, convenient for us. Okay, that's what we're calling them. One clock cycle is split into two, a positive half and a negative half, and a pulse width is the width of one half of the clock cycle. All right, we are concerned with the width of the clock cycle, or in particular with the width of a clock. The width of a clock cycle, because there are two things here, a rising edge and a falling edge, and with the beginning of a clock cycle we have a rising edge. Okay, we're going to be coming back to this later on. Now, the clock is quite important because we can create two types of circuits: synchronous circuits, which are controlled by the clock, and asynchronous, which are not. Asynchronous circuits are far more complex and therefore they are not used that often. All right, now let's get on to the most important thing, what the point of this, flip-flops. All right, flip-flops are called flip-flops because they flip between two states. All right, that's why we say that they contain a single bit, because a bit can be 0 or 1, and we are conveniently calling one of the bits state 0 and the other state 1. They also are referred to as a latch. Okay, and that's quite important if you think about the concept of a latch, because a latch holds something in a particular state. Okay, like a door latch holds this door open, and then when you change the latch, you apply an input to the latch, it then changes the state of the door and the door will shut. Door will now be closed. Okay, so we'll kind of you may hear flip-flops referred to as latches because they're holding a particular state. So this is an example of an SR flip-flop. Okay, I don't know why there's a flip equals flop there, but anyway, so the S and the R we're referring to set and reset. Okay, there are two outputs, Q and Q bar, but we by convention's sake read the output from Q, okay, not from Q bar. You can also see that kind of feedback within the circuit. All right, and that's quite important because that's what allows the flip-flop to maintain its state internally. All right, NSR flip-flop has a problem, right? So this is a low level activation. Okay, I think that's what we call it. And basically that means that in this one we are not allowed to have an input of S equals 0 and R equals 0, right? It's illegal to basically apply that input logic to this type of flip-flop circuit. Wow. Now what does this look like? Oh, the other thing to think about to say here is that flip-flops basically they work on pulses, right? It's not a constant input into S and a constant input into R that we are concerned with here, all right? Now if Q is 0 and Q bar is 1, okay, you can see the Q from 0 feeding into the bottom logic circuit. We have a 1 and a 0 going into that NAND gate, which is going to give us a 1 output, all right? That 1 from Q bar is feeding into the top logic gate, all right? That 1 and 1 going into NAND gives us a 0 at Q. So you can see that that feedback going round the circuit basically is maintaining that internal state. So we have Q is at 0, okay, as our output. Now what happens if we apply a pulse of at S? So we apply a low pulse, all right? Now basically a 0 and a 0 from Q bar going into the top logic gate, 0 and 0 in a NAND gives us a 1 as an output at Q. Alright, so you can see that by pulsing set, we've actually set the logic gate to 1. The 1 from Q feeding into the bottom logic gate, a 1 and a 0, so 1 from R and a 0 from Q going into the bottom NAND gives us an output of 0 at Q. Right, now once that pulse has happened, the circuit then returns to its default high input on both lines. Alright, so that 1 and 0 from Q and Q bar respectively are just going to keep now going round and round, and the SR is going to basically maintain its state at an output of 1 at Q. Now what happens if we receive another pulse? This time we receive the pulse at R. Okay, so a low pulse coming in at R, where we've got 0 from Q and a 0 at R going for a NAND gate. 0 and 0 gives us an output of 1 at Q bar, but that 1 from Q bar going into the top gate, alright, so a 1 and a 1 going into a NAND gives us a 0 at Q. So you can see how applying a low pulse at R basically will then will reset the gate, okay, reset the flip-flop so that we now have an output of 0 at Q. Remember, we're always reading the output from Q. So then we obviously, once that's done, we go back to pulsing a 1. All right, we go back to the default high state, and that internal state of the flip-flop of a 0 at Q is going to be maintained. Just bear in mind that we have this problem with an illegal invalid input of a low and a low, which is not allowed. Alright, now you can see here basically the flip-flop how by pulsing the one of the two inputs we are able to change the output from 0 to 1, and you can also see how a flip-flop is kind of maintaining its internal state. Now the main type of flip-flop that we're concerned with here with A-level computer science is the D-type flip-flop. Alright, a D-type flip-flop's got two inputs. It's got a data D and it has a clock. Alright, it's a positive edge triggered flip-flop. What does that mean if it's a positive edge triggered flip-flop? Alright, basically it's storing a single bit, alright, but the value of that bit can only change at the rising edge of a clock cycle. Now a D-type flip-flop, this is the truth table for it. It overcomes the disadvantage of an SR flip-flop where you don't have this invalid illegal input of a 0 and a 0, okay, but what you do have is you have two states where the flip-flop doesn't really care about what's going on. Okay, now you're going to see how this works, okay, in relation to the clock cycle, because we're now dealing with the clock being the thing that can change the state of the flip-flop and the output of Q, and we call this a tracking transition because the change in Q will only ever occur at the next rising edge of the clock cycle. There's lots of fireworks kicking off outside. Alright, now when you see a question on this, you will see the clock, alright, pulses, regular wave, square wave, and you will also see a waveform for D, and you will be asked to create the waveform for Q, stating whether the flip-flop is going to be outputting a high or a low. Okay, I'm just going to step through it bit by bit to build the complete wave for Q, sorry, the state of Q. So and you can see how I'm doing it. Now the first thing that I do is I mark off all the highs, all right, so I don't get mixed up when I'm tracking where the value of Q is going to change, the output, all right, because I'm only ever going to make any changes when I'm at the rising edge of the clock cycle. Now say I start off my waveform for D, all right, D is there, all right. Now what I want to do is I can see it's at a rising edge, therefore Q will go from low to high at that rising edge. If D continues, all right, and then it dips over there at that third rising edge, well, guess what? Q is going to do the same thing, because a change in D will only result in a change at Q if it's at a rising edge. Now, what happens if D changes part way through a clock cycle? Well, that's where that whole thing about a tracking transition comes into play, because basically nothing is going to change unless the change nothing's going to change until the rising edge occurs, okay, at which point the output of Q will catch up. So here, this is why you can see another name for a D-type flip-flop. Some people call it a data-type flip-flop. Some people say the D stands for delay, and the delay is here because the change is not propagated through until the rising edge of the clock cycle. That's one way of keeping things in sync, all right. Now a third thing that might happen is this: what happens if D fluctuates in between two clock cycles? Well, guess what? We don't care, because that change didn't occur at the rising edge. It wasn't noticed, all right? Therefore, the output Q does not change. Okay, so three things in here to bear in mind. First one is that the change in D only results in a change in Q when it occurs at that rising edge of the clock cycle, all right? Second thing, what happens if the change occurs part way through a clock cycle? Well, it doesn't matter, because what we are concerned with here is the fact that the rising edge will track the transition, and it will catch up. Q will catch up at that point. Final thing to think about is what happens if there's a fluctuation part way through a clock cycle. Well, nothing, okay, because it was high and high at the first rising edge and at the second rising edge as well. Therefore, Q will stay consistent. All right, so three things to bear in mind over there. So the way I do it, okay, first one is that I mark all the rising edges, so changes in Q are easy to pinpoint. Then I track I bear in mind, I think about the tracking transition, so changes are only occurring any time I'm in line with an arrow, okay, at that rising edge, and I ignore any fluctuations in between those rising edges. Now D-type flip-flops basically are storing a bit, all right. So if I've got 8 flip-flops of them together in a circuit, then I can store a byte. So you can imagine I've got 1 byte, 1,000 of those, 8,000 D-type flip-flops will be a kilobyte, and then 1,000,000, 1,024 times 1,024 will give me a megabyte, etc., etc. Okay, we use D-type flip-flops to create CPU registers and SRAM. They're not really used to create RAM, because RAM basically is made of capacitors, all right. So you have leakage, they need to be refreshed. RAM is quite, the capacitors can be quite compacted together, okay, to make densely packed circuitry, so you can get a lot of RAM onto a small chip. Okay, SRAMs basically you can't do that. They're not as densely packed, therefore they have a higher cost because they're more complex. So they're not used for high capacity RAM, because you would need to have more RAM sticks to have the same capacity, and it would be significantly more expensive. Okay, the main advantage of flip-flops, D-type flip-flops, is that the values are always there because of that latch function, okay, functionality. So therefore you have faster performance, hence the use of SRAM in cache and CPU registers, all right. So there it is, right? You should know what sequential logic is, and you should as in like the output being a function of the sequence of inputs, and you should have an idea of what flip-flops are, the fact that they are maintaining their state until there is a change in one of the inputs, and you should be able to explain how a D-type flip-flop works in conjunction with the clock in order to state what the output Q will be. All right, video on adders coming up in a couple of minutes.